Okay, everybody. So what we're going to be working on today is integrals of sines and cosines. Specifically, like when we have a bunch of mixed sines and cosines that are being multiplied together. And the way this works, you're going to need a bunch of trig identities, which you can see here. And also it's just a bunch of special cases. So we're going to have to go like, oh, okay, well, there's sines and cosines, and the cosine has an odd power, and so we do this. Or, well, it's just a sine, and it has an even power, so we have to do this. And that's just the way it is. There are no real, shortcuts to these, okay? So you're going to need a bunch of identities, and you need to be able to identify the type of problem that you're doing. Okay, now all of these identities here are just basic trig identities. You can get these from there's a in the notes and notes and worksheets, notes and handout section of Canvas. In the getting started module, you can find a trigonometry handout cheat sheet, and it has all of these formulas plus a lot more. I'm just putting them right here so that way you can copy them down without having to go somewhere else. Okay, so that's mostly it. The ones up here are what are they? Those are the top ones are just the Pythagorean identity that I rearranged two different ways. The ones here I didn't label. They're the half angle identities or the double angle identities. One or the other. That's why I didn't write down what they are. So there's no written evidence of my ignorance. We have the product to sum formulas. I do know what those are called, so that's why I labeled them. That's what these are down here. We're not going to need those for a little while. And then finally over here on the left, we have just kind of some miscellaneous things that we may or may not even use. But they're there anyway. So the ones on the right we definitely are going to need today. And so you need to have them written down. All right. Having said that, let's go ahead and get started. So the idea is when you have an integral like this, sine to the m, theta, let's just put an x, why not, it doesn't matter. Cosine to the n, x, dx, then how you do it depends on the exact powers. Like what you do or how you do it. The powers. All right. So before we really get into what the rules are, I'm going to show you an integral. Okay, so here's an integral that will be very quick to solve. So let's say I have a sine to the fifth x, cosine x, dx. So if you had this integral right here, what you would do is you would just do a simple U-Substitution. You would just say, let u equal sine x du equal cosine x dx. Then you'd be able to come up here and put in your U-Substitution. Sine to the fifth of x becomes u to the fifth. And the cosine x dx simply becomes du. And so that substitution really takes care of this integral quite easily, because then you just use the power rule, u to the sixth over 6 plus c, to do the integral. And then for your final answer, you just have to substitute back in your u equals sine x. So you have sine to the sixth x over 6 plus c, and that's your answer. All right. So that's is it very easy? It's either very easy or moderately easy or some kind of easy. It's easy. All right, it takes one line. If it's a nice wide line with several equal signs. But the idea is that we can do this for some other integrals too, if we can make them look like this integral. Okay, so the procedure will be as follows. So I really want to have an example to follow along, because if I write down the rules without an example, the rules will be very like convoluted sounding, and we'll still have to do the example anyway. So here's an example. All right, so if your integral, well, basically we're always referring to this up here. So if m or n is odd, okay, if m or n is an odd number. So this is our example. We're doing an example one. So let's just say sine to the third. Yeah, let's do the sine to the third x cosine squared x dx. Okay, now we wouldn't be able to do this, the kind of substitution that we did above on this one, because you know, if the du was like cosine x, we have two cosines and that would be the problem. Okay, so you can't just blindly do the same thing we did above for this one. It needs a bunch of algebra work, and that's where the trig identities come in. So if m or n is an odd number, like in this example, what are you going to do? I'm going to actually box this to make it easier to find later for you guys. Then what you want to do is separate one of the odd powers off to the side. Not one of the odd powers, one of the functions with an odd power. So since sine, in this case, has the odd power, separate a sine x dx off to the side. Off to the side. Okay, put a box around that. What am I doing? Try again. I'm going to try again. Works best when I draw a whole box. All right, so you want to separate a sine off to the side. That's what you want to do. So what that will look like is, what color was I using? This one. Since sine's the odd power, no, not that color. That color. Yeah. So what you're going to do is separate just one sine off to the side. Right? So this is what we just did. Now we didn't change the problem, right? There's still three sines, right? Sine squared times sine is sine to the 3. It's just that I'm taking one of them and I'm moving it to the end of the problem. Okay? Now, think about this. If you started with an odd power, right? Odd power, and we take one of them off to the side, like we did here, then what is left must be an even power, right? Of course it must, right? If you have an odd power and you take one away, now it's even. So what you want to do now is convert the rest of the now even power cosines. No, they're not cosines, those are sines. Sines into cosines using the Pythagorean identity. That's why we have those identities written down. Pythagorean identity. Right, so what is it for this problem? Well, we're using the sine version, so we're going to be looking at this version right here. So that's how we're going to convert sines into cosines with that. So, yeah, I'll write it here. So we're going to use this formula. All right. Put a box around that, and then let's do it. Really? That's interesting. Okay. So that is what we need to do, so let's do it. So we're taking this sine squared, and we're going to rewrite it as 1 minus cosine squared. So we're going to have 1 minus cosine squared x, cosine squared x, sine x dx. Okay? So there we go. Now, if you look at what happened, there's only one single sign left in the problem now. And because there's just one single sign right here left in the problem, that one that we saved off to the side, we're basically going to be able to do the procedure we did for this first example. Now, the one that's saved off to the side, like notice how I have cosine underlined here? The cosine was saved off to the side in order to be the du. Not the u, the du, right? The one that you have all over the place, in this case the sine, like where there's 5 of them, that's the u. So down here on this problem, cosine would be the u. All right, so now we should be able to use a substitution. Use a substitution. What you saved off to the side is not the u, it's there to be the du. Now I'm going to say is the du, right? Because depending on what kind of constants you have and whether there's pluses or minuses, it's not going to be exactly equal to the du, but it's going to be very closely related to the du. So use this. We're going to use this substitution in this case. So we're going to use u equals cosine x. Okay, so let's actually do that. So we've got u equals cosine x. So the du would be negative sine x dx. Now this is a regular u substitution here, so you have to handle any kind of constants you have properly. Like if it was cosine 3x, then the derivative, like if it was this, if you had a cosine 3x, then the du would be, you'd go negative sine 3x times 3, and then you'd have your dx. And so you'd have that extra 3 there, right? So keep that in mind. You have to actually do the u substitution properly here, but this will be the correct one. You still have to do it. All right, so we have this. I can take that negative and just move it to the other side where the du is, like that. And now we can make our substitution because we've got u is cosine x. So here's a u squared, and here's another u squared. And then we've also got negative du is sine x dx, and so that's what's right there. So we go ahead and we make the substitution. We're going to have the integral of 1 minus u squared, right? If u is cosine, cosine squared is u squared. And then we have another cosine squared, so that's another u squared. And then we have sine x, which is negative du. All right? And now we should just be able to integrate this like normal. Of course, we have to do a little bit of simplifying, but now we can integrate like normal basically. So I'm just going to say simplify and integrate as normal. And this should go just fine. Whoa, that's not what I wanted. Okay. So what's that look like? Well, basically what you want to do is you want to distribute this u squared out before you try to integrate. So if you distribute the u squared, you're going to have u squared minus u to the fourth du, and that negative on the du can just come out here, out of the integral. And from there, we're going to just find the antiderivative. So u cubed over 3, u to the 5 over 5, plus c. Now if you want, you can distribute that minus sign through. I will, because why not? And it'll change the sign of both of these, which means I should just change the order in order to write it nice. And from there, you just need to substitute back in your what u is equal. So sub back to the original variable. Okay, so all we got to do is write our answer then. So it's going to be u to the fifth. What's u? Cosine x. So cosine to the fifth x over 5 minus cosine to the 3x over 3 plus a constant. And that is going to be my answer. Done. Okay. And so that process is basically how you handle any kind of case where you have sines and cosines and one of the powers is odd. Now, everything is going to be reversed, though, if it's the cosine that has the odd and not the sine. Okay, so could be completely backwards. So let's do one more of these and a little bit faster. So example. So what do we want to do? I said it'll be a little bit different if the cosine's odd, so let's make the cosine odd. So let's go sine x, sine squared x, and then let's do cosine, instead of to the 3, let's do this to the 5, and that'll cause a little bit of an issue. Not too much. Actually, I'm going to change this x here too. Sorry. So we're going to go sine squared, and let's say 2x, and cosine to the fifth 2x dx. Okay. So let's go through the process. So you need to recognize that there's an odd power. So you save a cosine x, or in this case, cosine 2x. So save a cosine 2x off to the side. So you have sine squared 2x, cosine to the fourth 2x, and then cosine 2x dx. All right. Now what we're supposed to do now is we're supposed to convert the remaining cosines into sines using the Pythagorean identity. So convert the other cosines, the ones left behind, to sines. And how are we going to do that? We're going to use the identity cosine squared theta equals 1 minus sine squared theta, right? It's the same Pythagorean identity, just rearranged compared to the last one, right? When we did it up here, it was sine squared theta is 1 minus cosine squared. And here it's cosine squared is 1 minus sine squared. All right, but probably you see what the issue is, right? That this is a cosine squared here, but that's a fourth power up there. So it doesn't match. So what you have to do in order to substitute that in is you have to actually rewrite the cosine to the fourth, and I'm just going to say rewrite cosine to the fourth theta as, and I'll show you what to do right here. So that what you're going to do is you're going to rewrite cosine to the fourth as cosine to the 2, put extra parentheses around it, and an extra squared. So do you see what I did? I changed it into, trying to get a color here. right? So that's what I did about that fourth power. You write it as something squared squared using, regular valid algebra rules. All right, so we rewrote the cosine to the fourth, and then now we can use our identity. So we have 1 minus sine squared theta. Actually, it's not theta. What is it? It's 2x. Like that. And then we have a cosine 2x dx. All right. So there we go. So that extra second power, or the fourth power, was an issue. If it was a sixth power, we would have even more of an issue, but it's not, thankfully. So let's come up here. What we're going to do now is let's make our U-Substitution. We have to multiply this out, but it'll be easier to multiply out when it's all in terms of U. So we're going to use U equals sine 2x this time, right? Sine instead of cosine, and 2x because that's what we have, is a sine 2x. Du is going to be cosine 2x times 2 for the chain rule, and then dx. You're going to want to move that 2 over to the other side and write it du over 2 is cosine 2x dx. And now we're ready to make our substitution. So we make our substitution. So we have, what do we have? We have sine squared. So sine squared is going to be u squared. Then we have 1 minus sine squared 2x and the 2. So be careful there. Parentheses, 1 minus u squared squared. Is that what I want? Yeah, I guess it must be. And then the last part, we have, scribble over it. We have cosine 2x dx, which of course is du over 2. So we say du over 2. Now we can integrate, but before we integrate, we have to just multiply this all out. So you multiply this all out, you're going to get integral, keep the u squared there. This just needs to be FOILed, so it's going to be 1 minus 2u squared plus u to the fourth, and then du, and I can take the over 2 out in front, like that. So I have 1/2 integral. Then you can distribute the u to the 2 through here, u squared minus 2u to the fourth plus u to the sixth du. So you see that that's that's more work, right? We just had to multiply out more stuff. We had to rewrite it in the first place. So I mean, these are more trouble, but it is what it is. This is how you do them. So we get to here. Now there's nothing that stops us from integrating though. So we can just integrate. So keep the 1/2, u to the 3 over 3, 2u to the 5th over 5, u to the 7 over 7, and then plus c. And all that's left to do is write our answer, which I think I can fit it on this page. Right? That darker line there is the bottom, but we'll do it. So let's see here. I'm going to do two things. I'm also going to distribute the 1/2 on every term. So let's see. So what's u, first of all? U is sine 2x, sine. So if I'm going to rewrite this, I'm going to have sine to the 3, 2x, and 2 times 3 is a 6 in the denominator. And then I'm going to have minus 2 sine cubed. It's not cubed, it's fifth, isn't it? Get rid of all this, actually. 2 sine to the 5th 2x. Denominator is going to be 2 times 5, so that's going to be 10. And then we got the last one. It's going to be u to the 7th which is sine to the 7th 2x over 2 times 7, which is 14, and then plus c. I'm going to try to move this out of the way. Up a little bit. Okay. So, so that's our answer, I think. I think we're done with this one. Okay. So that's it. All right. And now we saw how to do it. 2 examples. So that's everything for when there's an odd power. Okay. Well, guess what? There's not always going to be an odd power, right? That's why I had to start this when I said if m or n is an odd power, then you do that. All right. So our next thing is going to be the integral of sine to the m cosine to the n dx when both powers are even. Okay, that's what we have to do next. Well, generally it's not going to be both of them. It's generally going to be just one or the other. So it's generally going to be like this. So I'm going to do a longer one just to show you kind of the scope of the annoyance on this, because they are annoying. Let's do sine to the 6th. I could put any number here. I'm going to go 3x dx. Okay, so first thing is you need to recognize that we're not in the previous type of problem, right? There's no odd power of sine, so we can't do it that way. We have to do it with new technique. So what's the new technique? So what you're going to have to do is similar to what we did here with this cosine squared. Cosine squared squared being cosine to the 6th. You have to rewrite this to see the a second power here. All right, and I'll even this is important enough to write it as a rule. I should have said second, and I said second power. All right, you need to rewrite it to see a second power. So it's going to look like this. Sine squared 3x parentheses parentheses to the 3. Okay. Now, what you're going to do there is you're going to take this and you're not going to convert it to cosines because that wouldn't do us any good. If you change this to cosines using like this type of identity, right here changes cosine squareds into sine squareds, or if you rearrange it, sine squares into cosine squares, right? But the power doesn't change, right? So if I changed this, if I changed sine squared into cosine squared, I would still really have a 6th power, and that doesn't help, okay? So if you scroll all the way up to our trig identities, you'll see that we've got other identities. So what we want is not this one, not this top one here, because that doesn't change the power. We want the one that changes the power, so we want this one right here. Okay, that will let the power go from 2 to 1, and that's actually going to be helpful for us. So we're going to apply that identity. So it's 1/2 parentheses 1 minus cosine 2 theta. Let's apply it. So we're going to apply sine squared theta is 1/2. I already forgot it. 1 minus? I think it was minus, right? Is that it? 1 minus cosine 2 theta? I have the memory of a goldfish. Yeah, 1/2 1 minus cosine 2 theta. Okay, so that's the identity that we want. Let me box that. So we apply that identity. We're going to get parentheses, where we got a different color here. Go back. So we got parentheses 1/2 parentheses 1 minus cosine 2 theta, but it's not 2 theta, right? Because we actually had a 3x. So it's actually 2 times 3x. So it's going to be 6x. And then a third power, and then dx. Okay? Now, here's the thing. Wait, hold on here. Is this what I want? I hope so. No, man. Okay, you know what? I'm just going to keep going because I don't remember if I don't know what this is going to do. It might be more complicated than I wanted, but I can't think about it because I'm not smart. So what you're going to do is you're going to work out this exponent here. And I made it a 3 instead of a 2 because I was trying to make it harder, but I regret that now. So we actually need to work out this exponent. So work out, so I mean multiply out the exponent there. So that's what we're going to do. We're going to multiply that all out. Now you do have 1/2 to the 3. That can just come out. But then you have 1 minus cosine to the 6x cubed dx. Okay? And that's not nice, like I said, but it is what we have, so we're going to go with it. So you have to multiply that out. So I'm not going to multiply it out there. I'm going to multiply it out here. So just think about it about this. 1 minus a cubed. Like, how would that work out? So let's just work it out over here. So that's 1 minus a, 1 minus a, 1 minus a, right? And you would FOIL the first set, and you would get 1 minus 2a plus a cubed, and then you'd have 1 minus a. And then you would multiply this out. So you're going to multiply the 1 by everything and get 1 minus 2a plus a cubed. But then you're going to multiply the a by everything, and you're going to get minus a plus 2a squared minus a to the... Oh, okay, there's a mistake here. Sorry. I don't know why I put a 3 there. That's a 2, right? Sorry. Let's rewrite this previous line here. All right, so multiply the 1 through, you get 1 minus 2a plus a squared. Squared, not cubed. Then you multiply the minus a through, and you get minus a minus 2 plus 2a squared, and then minus a cubed. Or if you collect like terms, you've got 1 minus 3a plus 3a squared minus a cubed. Okay? So like that. Now that's a lot of work, but if we come back over here, what we're going to do with it is this 1/2 to the 3rd power is 1/8. And then you've got the 1 minus cosine 6x cubed. But the cosine 6x cubed was what I called a over here. So if I write it out, it'll be 1 minus 3a, which is 3 cosine 6x. And then plus 3a squared, that's going to be plus 3 cosine 6x squared. And then we have minus a cubed, which is minus cosine cubed 6x. Okay. Fun, right? Um, Now, here's the problem. I strongly regret using a sixth power. I should have, like, honestly used a 4 or an 8. 6 is pretty much worst case scenario here. But let's think about what we have. So I can integrate the 1. That's okay for integration already. I can integrate the cosine 6x. That's okay for integration already. Now, over here we have a cosine cubed. Now, how do we do cosine cubed? Well, we actually know how to do cosine cubed because we just learned how to do odd powers. So we have to use our previous method on that, but we could do it. But this right here, the cosine squared, that's still an even power. Well, that's not nice, but it's an even power. So how are we going to deal with the even power? Well, what we're going to have to do is we're going to have to take this even power and we're going to have to use this identity again, this kind of identity. But not the one for sine squared. We're going to have to use the one for cosine squared. And that's specific to this problem, okay? We could have gotten lucky and not needed it. But basically, any even powers, you still have to do this again, okay? So we're going to use, all we're going to do here is we're just going to use the same identity, but for cosines. So 1/2 1 plus cosine 2 theta is the identity we're going to use there. And let's write this all out. We got 1/8 integral 1 minus 3 cosine 6x. Here's where we're going to use our identity. So our identity is 1/2 1 plus cosine 2 theta, but the theta, right, the theta is the 6x. So 2 times 6x is 12x. So we use our identity, and then we just have this cosine cubed here in the way, taking up space and being annoying. All right. So let's see where we are. We've got 1/8 integral 1 minus 3 cosine 6x. Let's multiply this out. Plus 1/2 plus 1/2 cosine 12x minus cosine cubed 6x dx. Well, what can we do? First thing I'm going to do is I'm going to rewrite this one more time. All I'm going to do is I'm just going to collect the 1 and the 1/2 here together. So 1 plus 1/2 is just 3/2. And then I have minus 3 cosine 6x plus 1/2 cosine 12x. Like that. And then this cosine cubed, I'm going to move off into its own integral using properties of integrals and have minus 1/8 integral cosine cubed 6x dx. All right. Now, in this section right here, where we've got a cosine 6x and a cosine 12x to integrate, that's actually going to be really easy because all you're going to need to do is you're just going to need to remember that if you have to do the antiderivative of a cosine of like kx with a constant there, it's just sine kx over the k. So it's not hard to handle the 12 and the 6. That's pretty easy. So that's not going to be an issue at all. Okay, let's actually do that integral then, and I'm going to kind of ignore that cosine cubed over there for a little bit while we do this one. So I've got 1/8 parentheses, and I need to integrate each of these terms. So I've got 3 halves. How do you integrate 3 halves? Well, 3 halves dx, the integral is going to be 3 halves x. Then you need to integrate the minus 3 cosine 6x. So you're going to have minus 3 sine 6x, and then you're going to have to divide by the 6, according to my formula right there. Then we've got to do the cosine 12x. So I've got plus 1/2, and then the antiderivative of cosine 12x is going to be sine 12x over 12. Again, not a tough integral there. Okay? And so we get that. Now, before we go any further, I just want to point out that this whole thing over here, the cosine cubed, the only reason we have that is because of my poor choice of a sample problem where I used a 6th power. Generally, the first one that they give you is a 4th power, and if they want you to do a long problem, they usually give you an 8th power. They usually don't give you a 6th power, and we're seeing why, because it results in this 3 over here. But what we did here on the left is the main point of what we're doing, okay? Having said that, we still have to finish this 1/8 cosine cubed here. So we should be able to do it quick because we know the method from the previous section, really. So what do? We split it up, right? We split 1 off to the side. That's what we just learned. The cosine squared, we use the Pythagorean identity on and get 1 minus sine squared. Like that. Then you need a U-substitution. U is sine 6x. du is 6 cosine 6x. dx. That's a dx. So du over 6 is cosine 6x dx. So our integral there is negative 1/8 integral 1 minus u squared du over 6. Okay. I think we can finish it right here, so let's do it. We've got the 6 and the 8. Let's just combine those and get negative 1 over 48. Let's do the antiderivative here. The antiderivative of 1 minus u squared. The antiderivative of 1 is u, and the antiderivative of u squared is u cubed over 3 plus c. And then you need to substitute in your u, and you get negative 1 over 48, u, which is sine 6x, minus u cubed, which is sine cubed 6x over 3, and then plus c. All right, so that was tedious, right? So what's our answer? So what our answer is going to be is if I take this 8 and I just kind of distribute it through here, we're going to get 3 over 16x. Then we're going to get minus 3 sine 6x over 6, over 48, which can be simplified, but I'm not yet. Then here I've got 2 times 12, which is already 24. 24 times 8, is that 192? I think that's 192. So I think we have sine 12x over 192. 24 times 8. Yeah, I think that's right. Okay. And then we've got these two terms over here. So I've got minus 1 over 48 sine 6x. And then 48 times 8. What? It's impossible. Okay, 48 times 8. Okay, it's not actually impossible. We can just use a calculator. 384. So I've got minus 1 over 384 sine cubed 6x plus c. So all of that. Now, let us write our answer now, because I have to rewrite it because there's like terms, not those. These are like terms, right? They're both sine 6x's. So if I want to write my final answer, I have 3 over 16x minus, I've got 3 over 48 minus 1 over 48. So that's minus 4 over 48. 4 over 48 is 1/12 sine 6x. And then plus the sine 12x over 192. And then I've got the 1 over 384 sine cubed 6x plus c. Yikes. Now, let me just box this and say something. So, that was tedious, right? The main thing you want to know about this is that up here, when we were doing the odd powers weren't so bad. Like, it takes several lines of work, but otherwise they're not so bad. The even powers are kind of annoying. You use different identities, and you get everything down to the first power, basically, and then you can integrate it. But if you ever get to a point like we got to here, where is it? If you ever get to a point like you have here, where you've got some even powers and some odd powers, you've got to handle the odd powers the way you did in the previous problems. It's just how it is. Keeping track of your work and doing this in an organized way is the key to getting it right. Okay? Yeah. So those are long, complicated. You only have a couple to do that are this hard. Maybe not even a couple, maybe just one. But it is what it is. So that's what you do when you have even powers. Next thing. Okay, so let's do, let's see here. We did that. I guess really we just have the product to sum one. So let's do something easy, like, to cleanse your palate after that. So a difficult problem, not a difficult problem. Easy problem. What we're going to do now is, when we have, I don't even know, I'm just going to say product to sum problems. Product to sum problems. All right, so what are these going to look like? They're going to be pretty obvious. They're going to look like, just box that, and let's color it in. Can we color in the lines? Probably not, huh? I'm not competent for that. Nope, see, couldn't do it. Product to sum. So what are we doing here? So the idea is you're going to have an integral that looks like this. So an integral that's like sine ax cosine bx. So the implication is that those are different numbers now, the a and the b. Or you're going to have, you could even have sine ax sine bx. Or you could have sine, cosine is what we didn't do, right? Cosine. Right? So there's only 3 possibilities. If you look at the identities up at the top, I wrote 4 identities for product to sum. But if you look at the last 2, right, really the last 2 are the same. It's just which order you write them in. So I'm not going to count those as different types of integrals. But it is good to have the formulas for all four so you don't even have to think about rearranging terms or anything. And these are really straightforward. All you're going to do is just, step one is going to be use the right product to sum identity. Use the product to sum formula. Step two, integrate. That's it. So they're really, really a much easier thing than what we just did. And that makes them nice. So let's do an example. So let's do an integral of, let's just, I don't know, it doesn't even matter, right? So let's do sine 9x, not minus, times cosine 4x dx. Okay, so all you're doing on these is you're just thinking of this right here as being your alpha, and you're thinking about this right here as being your beta. And you just want to use the formula that has a sine and then a cosine. So I'm not going to scroll all the way up because I have them written down right here, but you have this identity. So we have sine alpha cosine beta is 1/2, parentheses, to have room, 1/2 sine alpha plus beta, and then plus sine alpha minus beta. Okay, fit barely. All right, that's it. So all you have to do is just say, well, alpha's the 9x and beta's the 4x, and then work it out. So very straightforward. We're going to have, I guess I was using green. Not that green. That was the green. All right, so what are we going to do? We're just going to have this. So you just go 1/2, parentheses, sine alpha plus beta. Alpha plus beta is just, I'm going to write it out, 9x plus 4x. But 9x plus 4x is just 13x, okay? So don't think this is complicated. It's not. And then sine alpha minus beta, that's 9x minus 4x. So you get 1/2 integral sine 13x plus sine 5x dx. So that's it. A very easy integral now, because all you have to do is basically the way we did this. You just do that again. We have sines and not cosines this time, but it's still a basic antiderivative. So we're just going to integrate. We just get 1/2 parentheses, and we're going to get, what are we going to get? So the antiderivative of sine is negative cosine 13x over 13. Then the antiderivative of sine is negative cosine 5x over 5 plus c. That's it. Done. You can multiply the 1/2 in there if you want, or not. I choose not. Okay, that's it. All right. I do want to do one more of these just as a little bit of practice, because there's one thing that we didn't see here. So the one thing I want to see here is, let's do this one. Let's go sine. Let's go sine 2x sine 5x dx. Okay? Now you're going to need the formula again. So we need the one for sine now. So sine is, according to my writing here, 1/2 cosine alpha minus beta minus cosine plus beta. Okay, so there we go. That's our identity. So we're just going to apply that identity. Apply identity. So we get the integral. 1/2. I'll put the 1/2 on the outside to start with. Cosine alpha minus beta. So that is cosine 2x minus 5x. I guess I'll write it again. 2x minus 5x minus cosine alpha plus beta, which is 2x plus 5x dx. So I'm just going to rewrite it. All I'm going to do is just add those. So 2x minus 5x is negative 3x. And 2x plus 5x is 7x. Right? And the reason I wanted to do this problem was because of that minus 3 there. This minus 3. That minus is a little bit weird. Okay? Now we can easily integrate this. So the integral is going to be, the antiderivative of cosine is sine. So sine negative 3x over negative 3. And then minus, the antiderivative of cosine is sine. So sine 7x over 7 plus c. And you feel like you're done, right? I'm going to multiply this out. So you feel like you're done when you see sine negative 3x over, I guess, 6, and it's negative. And then minus sine 7x over, looks like 14 plus c. So you have this, and you think you're done, but they don't really like this, having that minus sign inside of the sine. And that's why up at the top, when I gave you a bunch of trig identities here, I said, maybe also useful, and I gave you this and this. If you ever have a negative inside of your sine or your cosine, then you can do this. So if it's a sine, you just take the minus sign out. Let me get rid of this. So if it's a sine and you have a minus sign there, you can just take it out. If it's a cosine and you have a minus sign on the inside, you can just not write it anymore. Okay? So back down here, where we have a sign and then we got a negative in there, you can just basically take that minus and move it out front because of an identity. And when you take the minus out front on this example, it'll be a minus minus, which is a plus. So if you're comparing your answer to what the computer has, they probably have this. And you don't see any minus signs inside of a sine or a cosine. Okay, so just using that little identity. Which is just the fact that sine is an odd function. That's all it is. All right, so I wanted to do that before we stopped. So that's it for this. We're like 58 minutes into this video. There's another video coming where we do secants and cosecants, which is going to be pretty much just as much, sines and, I said secants and cosecants. Another video where we do secants and tangents. Same kind of thing, but more of it. So that's it for now. See you in the next video.